No, sir. I think we can start now.
We can start.
Yes, sir. Others can join later.
So welcome all to this webinar on power semiconductor industry conducted by IEEE Kerala chapter. Today's speaker is Dr. Akshay K. He'll be speaking on the topic power semiconductor industry, innovations and significance on India. So I'll just give a briefing about Dr. Akshay. Dr. Akshay K is a senior engineer at Micron Technologies NAND Device Technology Development Group. He received a BTech degree in Electronics and Communication Engineering from NIT Calicut in 2017 and an accelerated PhD in Electrical Engineering from IIT Madras in 2022 with Prime Minister's Research Fellowship. His research interests include the design, modeling, and simulation of flash memory cells, power semiconductor devices, and CMOS image sensors. He is a primary contributor in over a dozen publications in leading international journals and conferences. He is a recipient of the Institute Research Award issued by IIT Madras as a recognition of the quality and quantity of research done in PhD, and AWSAR Award issued by DSC Government of India for disseminating the research outputs of PhD among the masses in an easy to understand and interesting format to a common man. Besides the first rank holder in the Department of Electrical Engineering during his PhD, he received the Best Major Project Award of CREC PTA during his UG studies. Dr. Akshay was also active in the student branch activities of IEEE. Besides being a member and volunteer of IEEE during his UG studies, he was the founder and chairman of the IEEE Electron Devices student branch at NITC during 2015 to 17. Welcome, Akshay, sir, to this talk, and over to you, sir. Sir, you're not audible.
Sorry. I was telling. Thank you so much for the detailed and kind introduction, and thank you everybody for joining, especially on a Sunday evening. I sincerely hope I do justice to your time as well. So without further ado, let's just get started. Can you confirm whether my screen is visible? I'm clearly audible?
Yes, sir. It is visible.
Okay. Thank you so much. So should I turn off my video to save bandwidth? What do you feel?
Sir, it's not okay.
Sorry?
Okay, the video is okay.
It's okay, is it? Okay. So, as everybody knows, the topic for today's webinar is power semiconductor industry, innovations and significance in India. So what I'm going to do, let me take my pointer also so that it's easy. Okay. So this is going to be the brief outline of my talk. I'm going to initially give a very brief introduction to the area of power semiconductor devices. Then we'll see what is supposedly the holy grail for researchers working in this area of power devices. It's called the breakdown voltage specific on resistance design trade-off. I'm sure this might appear a jargon term to most of the people on call, but that's okay at this point of time. I assure you that I'll make you experts within 5-10 minutes on this topic. After that, we'll see the significance of overcoming this design trade-off for India. So essentially, as of now, you can think of this as two different parameters of interest for people working in the area of power devices. And these two are kept in mind while designing any power device. So that's the whole thing. So we'll discuss what is the significance of overcoming this trade-off for the Indian scenario, especially. Along which I'm going to show you a 2-minute video, which I myself shot while visiting an industrial power device fabrication facility last year. So as to just give a glimpse of to show you how things work inside the industry fabrication unit, especially a power device fabrication unit. Then we'll see what are the available solutions people have proposed in the past to overcome this trade-off. And finally, I'm also going to discuss this works means my PhD work or my research works. So contributions towards overcoming this trade-off. So some of the very key results I'm going to just at a very superficial level I'm going to touch. Then finally, I'll summarize the key points or key takeaways. So if you take power systems, the power systems ranging from generation of power at the power station, including renewables or non-renewable, whatever it is, to transmission distribution networks, all the way down to industrial and household applications, operate at a power level of anywhere of the order of a few watts to a few gigawatts of power. And depending on where we are looking at and what kind of application we are looking at, these applications typically employ any of these 4 different kinds of power converters: AC-DC, DC-AC, DC-DC, and AC-AC. And we all may not be familiar with the circuit level implementation of all the converters, but I'm sure that AC to DC is something which everyone is familiar with, right? This is a bridge rectifier. And as everyone knows, this is like we have these diodes which forms this bridge rectifier. And what we expect from this is one half of the sinusoid is blocked by the diode, and the other half of the sinusoid is just passed by the diode. So that's how the bridge rectifier works, right? So these diodes are not just employed in AC-DC converters. These are also employed in all other forms of converters as well. And the diodes which are employed in these systems we expect them to work, depending on the application, anywhere of the order of few hundreds of volt to tens of kilovolt in the off state, and expected to carry a few amperes to thousands of amperes in the on state. Just to reiterate, in the off state, what we mean is when we reverse bias this diode, apply a reverse bias across the diode, we expect the diode to hold off that voltage without electrically breaking down. We expect it to behave as an open switch. So that is why we are saying we want this diode to have a very high breakdown voltage in the off state. Whereas in the on state, when it's forward biased, we ideally expect it to be a short with zero resistance, but we all know that there's nothing that have zero resistance practically. So there will be always a non-zero resistance R-on associated with the device. And in power device area, we want to have as low specific on resistance as possible. So specific on resistance is nothing but just resistance multiplied by the area of the chip or area of the device. So for the present webinar and for this discussion, you can think of specific on resistance as equal to on resistance. Nothing. Just think of it as on resistance only. So let me explain the significance, the practical significance of these parameters, breakdown voltage and specific on resistance, by taking the example of an electric vehicle. So this is a very highly simplified, dumbed down example or illustration schematic of an electric vehicle. You have this battery unit. Here it's a 350 volt battery unit. It depends on the car company and the model and all those things, but still, let's for the time being take for 350 volt battery pack. And there's a switch which regulates this voltage transfer to the motor, and the motor of course drives the vehicle. So imagine that you can drive this vehicle in 2 modes. Okay, first is the no acceleration mode, wherein the driver do not apply any pressure onto the accelerator pad, and in that situation we want the car to be stand still, right? We don't want the car to move forward, which means that no amount of the battery voltage should be supplied to the motor. So, or in other words, this switch should be able to block the entire 350 volt across it. So in electrical sense, this diode equivalent should be able to block in reverse bias this entire 350 volt. So the switch that we use for this application should have at least 350 volt of breakdown voltage. For practical sense, we always keep it at much higher level, let's say 450 volt, to take into account all the voltage overshoots and for reliability purpose. But for the time being, let's say it should be more than 350 volt at least. So that's the first mode in which you drive the vehicle. And imagine that there's the other extreme. The other extreme is the full acceleration mode, wherein you want the entire 350 volt to be made available to the motor, which means that this switch should pass the entire 350 volt without any drop across it. But in practice, there will always be an on resistance associated, which will drop across it, and there will be a power dissipation, heat generation, which has to be what should I say, cool down. Okay. For instance, what I can tell you is Toyota, when they make electric vehicles, one of the challenges that they had faced a few years back was that they wanted to make these devices with a specific counter resistance of less than 1 million centimeter square. The reason being that when the specific counter resistance was much higher, they wanted to have this all these cooling systems, special cooling systems in their car, which makes the whole system bulky and expensive. And by making the specific counter resistance less than 1 million centimeter square, they could get rid of or they expect to get rid of the entire bulky cooling systems and reduce the cost and reliability also. So that's a practical sense, in a practical sense. So we had in detail looked into what is breakdown voltage and what is specific on resistance of a power device. And this is the important thing, that there exists a trade-off between these two parameters. And what I mean by that is that if you try to improve one parameter, the other parameter worsens. Okay. If you try to increase the breakdown voltage of this device, automatically the specific on resistance will also increase. Or in other words, if you try to decrease the on resistance, you will end up having a low breakdown voltage, but you want a high breakdown voltage in practice. So that is the trade-off. The reason for this trade-off, I'm going to explain in another 5 minutes. But for the time being, let's just take it for granted that there's a trade-off between these two parameters. And the relevance of this trade-off, or overcoming this trade-off in the Indian scenario, are as follows. Firstly, looking into the electric vehicle sector, our country is pushing for electric vehicle ecosystem, as everybody knows, in this decade. And being able to develop less lossy power devices would be a major boost for the in-house, would be a major boost for the success of this initiative. So that's the electric vehicles. And coming to the defense sector, we plan to ban the defense imports completely by 2025. It's a 4 lakh crore project, and in-house design and development of power devices is crucial in several of the military applications, including missiles, battle tanks, and submarines. For instance, while I was doing my PhD at IIT Madras, we had this DRDO projects coming in where they wanted to develop silicon carbide devices for various military applications. So there's this very strong motive towards going for in-house design and manufacturing of high voltage devices in India. And coming to the third one, which is the India Semiconductor Mission. Most of you would have seen this on the newspaper, because it came up in the first page itself when the government announced this a few months back. So this is essentially expected to be a 76,000 crore project, which aims to build, in quotes, build a vibrant semiconductor and display ecosystem in India. And this opens up scope for all the manufacturing thing across the semiconductor device spectrum, but specifically also for in-house design and development of power devices. And the current scenario is that there's only one private company in India that manufactures power devices from the wafer level. And they manufacture diodes and thyristors, not MOSFETs or other devices. So this is the company where I had also visited last year, and I'm going to show a video of the virtual tour of the fabrication facility there soon, or rather I'll show it right now itself. Don't know whether you will be able to hear the sound. Sound is not required. It's just a BGM to not keep you bored. That's all. Are you able to see the screen, this video thing? Can anybody confirm, please?
Yes, sir, it's visible.
Okay, so and I don't know the sound. Is there any sound that's coming up?
No sound, sir.
Okay, fine. So do you know how to share the sound as well? If I open it in a Chrome or something, will it show sound?
I am not sure about that one. I think
Okay.
this video is okay, and you can explain that one. So
Okay, is it? See, hear sound? Are you able to hear the sound? No, is it? Anyone?
no sound.
No sound, is it?
Yeah, but it's visible.
Anyway, it's not very important. Still, I'll just play it from the beginning. So this is basically a power device manufacturing unit that we have in India, in Gujarat. So I happened to visit the facility last year and for some research purpose, and I got to take some videos from there about how about the various processes that's happening inside the industry. But these are not all the clippings are not in sequence, which means that the entire starting from the beginning to end of the product is not there. I mean, step by step is not there, but approximately whatever I have clubbed it. So wafers are unboxed, which means that we'll procure the wafers from external vendors from outside usually, and they are depending on what the specification of the thickness and resistivity of the wafers we want, we procure it from outside, and there after unboxing we load it into a quartz board like this. Along with this is for diffusion basically. We want to diffuse the do some diffusion, and they are manufacturing thyristors and diodes mostly. So they need this P diffusion for the for making these diodes and thyristors. So what they're doing is that they are putting this inside a glass chamber along with a dopant source. In this case, they want to dope it. They want to dope this aluminum, which is a P-type dopant. So they are going to seal it. They are going to vacuum seal it by thermally. There are two glass surfaces you can see, which they are going to seal it by kind of welding. And it becomes so hot and bright that you would need special glasses to see through. And once you seal it, vacuum seal it, you have to take it very carefully because it's vacuum inside and it can burst out if there is any disturbance. So you have to very carefully keep it inside the oven for diffusion, which happens at somewhere around 1000-degree temperature. You push it deeper and close to the heat source, so that it uniformly undergoes diffusion. This is another step. This is not a continuation of that. This is another step, which is aluminum evaporation for metallization, for making contacts, right? So you have these chambers, then you have lithography units, exposing it to UV. Maybe BTech folks would not be able to appreciate it, but MTech folks and others would definitely be able to appreciate at least most of the steps, I hope. And there is passivation and final packaging and testing. That's the end. Just want to give you a very quick overview of what happens inside a fab. I know it's not in proper sequence, but whatever video clips I had, I just edited it and gave it. So coming back to the presentation, that was slightly off track, but anyway, I feel that that's important. So coming back, we were discussing about the breakdown voltage specific on resistance trade-off. Now, as I told you before, I have not explained why there is a trade-off. I told you that there is a trade-off, but we have to know why, right? So for that, let's just consider a simple conventional PN diode. So this is a PN junction diode, a power PN junction diode, and that usually has a P plus, a thin, highly doped P layer, a relatively lightly doped and thicker N layer, and then this N plus substrate. So that's how the structure of a simple PN junction would be. Diode would be. This N layer is kept thick because the voltage is supported across the in the N layer. So that's why it's kept thick. So when you apply a reverse bias voltage across this diode in any application, when you use it as, let's say, in an AC to DC converter, so, sorry, during one half of the sinusoid, it has to block the voltage, right? So when that when some amount of reverse voltage is applied across this diode, what happens is inside the device, you have this space charge extension. That is the space charge or the depletion region extends. More amount of positive charge or ionized donor ions are exposed, and electric field lines from each of these positive charge moves in towards the ionized negative acceptor ions in the P plus. So I hope people with devices, some basic device course would be able to appreciate this slide. So that's how a diode will be able to block the voltage, right? And if you plot the electric field distribution, corresponding electric field distribution, it looks something like this. So here, for instance, there is no charge and hence there is no field. And as you go more and more closer to the interface, you start seeing more and more electric field lines, right? Because more and more charge, more and more electric field lines. That's why the electric field gradually increases. And the maximum electric field is seen at the junction, because all this positive charge emanates electric field lines, and all those electric field lines are seen at the junction. So that's why you have the highest electric field at the junction. So then this results in an triangular electric field distribution. Now, when you keep increasing this reverse bias across this diode, there comes a point where this electric field at the junction increases to a value, we call it as critical electric field, and that is a material dependent quantity. For instance, for silicon, around it comes around 300 kilovolt per centimeter. So around that kind of electric field magnitude, what happens is that the device breaks down, electrically breaks down, and you can't apply any more further voltage across it in reverse bias. So that's what it means. Now the question is, how do you increase the breakdown voltage in this scenario? Okay. Now, one way of increasing, or the two ways that we have for increasing the breakdown voltage, is to reduce the doping and increase the thickness. Why? When you reduce the doping, what happens is that this slope is there, right? So this slope, if you reduce the doping, the slope will also be lower. That means the electric field will decay down slowly. You have a higher area under the curve, right? And an area under the curve is nothing but the breakdown voltage. So if you reduce the doping, you have a higher breakdown voltage. And also you need to have sufficiently thick layer so as to support that voltage. So decreasing doping and increasing thickness will give you high breakdown voltage. That's the summary. But on the other hand, this will lead to high on resistance, right? Because lower the doping, higher the resistance, and higher the higher the resistance. And if you increase the thickness also, you know that resistance is proportional to the thickness, right? And then that also leads to high resistance. But on the other hand, if you want to reduce the on resistance, you need to have high doping and low thickness. So basically what I mean to say is that the requirement is contradicting. Here you want lower doping, here you want higher doping, here you want higher thickness, here you want lower thickness. So this requirement of this choice of these parameters is contradicting. That's why we have this trade-off between these two parameters. And the way people have gone about this trade-off, or pushed this limit, is as follows. One of the method is by making structure related change. And that is why we went from a simple conventional PN junction to what is called as a superjunction structure. And just by looking visually itself, you will be able to figure out the difference between the two. Here you just have P pillars inserted into this N region. That's the only difference that you have from compared to a conventional junction. So that's how you get a superjunction. And how does introduction of these pillars will improve the breakdown voltage? If you take in the few slides back, we saw this triangular electric field distribution for a conventional junction, right? If you take a superjunction, this gets modified into somewhat like this. Ideally speaking, this triangular distribution gets modified into a rectangular distribution, and hence much higher breakdown voltage can be achieved, because breakdown voltage is nothing but area under the electric field distribution. So that is how. So, I mean, this is how it is able to achieve a higher breakdown voltage. And how does this, why does superjunction have this kind of a rectangular field distribution? Can be explained as follows. You just consider one unit cell of this PN junction, PN superjunction, just one unit cell. This is a repetition of many cells, right? So just one unit cell you consider, it looks something like this, okay? And imagine an ideal case where the doping of the N and P pillar are exactly the same, and width of the N and P region are also exactly the same, which means that the charge in the N and P regions are exactly balanced. Imagine that kind of an ideal situation. In that situation, what happens is that when you reverse bias this diode, it is not just the vertical PN junction that grows in depletion. It is also the lateral PN junction. This horizontal junction also deplete each other, right? So this, the result of this is that once at a very low voltage itself, if you design the width of this junction to be very low, at a very low voltage itself, this charge will eat up each other. Okay. So once this charge will eat up each other, what happens is that for any higher voltage than this, the electric field lines that start from this N plus region will not see any charge inside this region. It appears as if there is no charge inside the region because it has already eaten up each other. So for any additional voltage, the electric field lines coming from this positive charge will be able to travel the entire length of the pillar and get terminated only on the negative ions here. Okay, so that is why you get very straight kind of an electric field profile. And this only if these lines get terminated on any of this charge, leftover charge here, there will be a slope. If there is nothing to terminate this field lines, there won't be any slope. So that's why you have approximately a rectangular kind of a distribution, and hence a high breakdown voltage for superjunctions. Now, the second way people try to improve the trade-off is by making material-related change. That is why people we are moving from silicon-based electronics, power electronics, to higher band gap-based power electronics, which means that we're choosing materials that have a higher band gap than silicon. And when I say higher band gap, that translates to having higher critical electric field also. It's not just silicon carbide. These days commercially a lot of silicon carbide devices are available already. And why I had put diamond and a question mark is because diamond is also being very actively pursued, researched upon by researchers across the globe, and mostly academic researchers. And it's in a very infancy stage as of now. And maybe a decade or so later, we don't know, we might have some diamond based power device in our day-to-day electronics also possible. But as of now, it's of academic interest only. So we have silicon carbide devices commercially available these days. So how does silicon carbide, how changing the material manifest in this electric field distribution? Let's look at it. Here is the breakdown field distribution of a silicon PN junction diode. If you simply replace the material, imagine this is the junction. So if you make this using silicon, this is the breakdown field distribution. Now you simply change the material to silicon carbide without changing any other parameter. You make it silicon carbide. What happens is you will end up having a much higher critical electric field, because silicon carbide can withstand much higher field, almost 10 times field than silicon. So that's why you have a much higher critical electric field. So that's how it's able to achieve larger breakdown voltage. Now, one of the thing that we did during my PhD days is we derived closed form solution for the design of a superjunction, both an ideal and practical case, which means that you take this device. Suppose you want to take or you take this PN junction diode. If you want to design this diode for a certain voltage, let's say 600 volt, the question is what is the thickness and the doping of the N layer that you choose. So these are the two important parameters that you need to choose for a given breakdown voltage specification. Similarly, if you look into superjunction, the parameters that of interest are the length of the pillar, the doping of the pillar, and the width of the pillar. So these three parameters, the value of these three parameters are to be decided for any given breakdown voltage. Okay. So that is the problem that we took up, and we derived closed form equations, which means that we could derive equations like this: L equal to W equal to N equal to, and all you need to do is substitute the appropriate breakdown voltage that you target for, and other things are all material parameters. And how I have derived these equations is beyond the scope for this webinar as of now. But let's just take it for granted for the time being. More details will be are given in this paper. So we have derived, and calculations of using those model will show that the specific on resistance for any given breakdown voltage, for be it silicon and silicon carbide or silicon carbide material, our model is predicting 30% lower specific on resistance as compared to the prior models. And thereby we could establish a new theoretical minimum of the specific on resistance, solving a 2-decade long problem. Why 2-decade long problem? Like the model previously published for for solving this problem was 20 years back. And since then there was a research gap in there, and people have been using the same model, that 20-year model since then, even recently. So by this model, we could establish new theoretical minima. So that's with the ideal superjunction case. And we had also shown calculations for other materials as well, just theoretical predictions, diamond, gallium nitride, so on. And the second problem statement, previously we saw an ideal junction. Now we had also solved for superjunction by taking into account process variation, which means that we had initially assumed the doping and width are exactly equal for the NNP pillars. We had also shown calculations where we allow an imbalance between the doping and width of the NNP pillars. And the imbalance factors called Kn and Kw is decided by the process variation, which means that ideally you want the N and P pillar to be to have the exact same doping and width. But when you manufacture, you won't be able to exactly realize the doping and width that you target for. There will always be slight deviations from what you target. And that deviation is being taken care of by this Kn and Kw. It could be, let's say, 0.1 or 0.2, which means a 10% deviation from N pillar or 20% deviation from N pillar and so on. So when you allow this flexibility, the whole equation, the way you have to solve everything changes. So that's the challenge. And if you look into the prior literature, methods available to design this kind of a device, it was essentially, they were proposing 3D search problems, which means you have to span the entire 3D space of you have to randomly vary W, L, and ND and search for an optimal solution. That's like a numerical iteration procedure with no initial guess, which makes it quite difficult to do it and time consuming also. We could reduce that to a set of closed form equations and thereby eliminating all the tedious iterations, and we could express it in a material independent form. Again, I'm not in a position to describe the entire procedure of how we derived it, but let's just take it for granted for the time being. So the method gives values for or equations for L, W, and ND. All you need to do is choose the right breakdown voltage for which you have to design, you are designing this device for, and you put in the right values of K and KW, which means that how much process variation you expect from your process, and the equations will give the value of these parameters that you need to target for. This is the model. Suppose you want to make a 2 kV device out of silicon carbide, a 2 kV superjunction from silicon carbide. So here is the 2 kV. You see what is the doping and the pillar length and width from this chart or from this model. So this is nothing but the plot of these equations. So you can use the equations in principle, but this is just a plot where we did all the calculations and summarized the whole result. That's all. And it is matching very well with ticket estimations also. So that was the first thing that we did. And then if you see, as I told you, things have been moving from silicon to silicon carbide. So initially you had PN junctions in silicon, then you had power diodes in silicon carbide, but silicon superjunctions have not been properly or commercially transferred to silicon carbide based superjunctions. You can see a lot of silicon superjunctions in the market from all the famous companies, but silicon carbide versions of the superjunction is still not up. It has been demonstrated academically, but there are a lot of challenges associated with making the P pillar for a silicon carbide superjunction. So that's the difficulty with silicon carbide based junctions. So we took up this as a problem, and the way we could propose at least a theoretical solution is by as a new device structure wherein we suggested replacing the P pillars with a bilayer of silicon dioxide and Al2O3. And what this combination does is that along the interface, along the trench wall, you will have a negative interface charge. And that interface charge magnitude can be controlled by the deposition temperature and all. And the function of this P pillar was just to eat up the N pillar charge, right? As I explained to you before, the function of the P pillar is to just to eat up the N pillar charge. So if you provide the equivalent amount of P pillar charge using this interface charge, then the requirement is satisfied here also electrically. So that is why, but on the other hand, you don't have the difficulties associated with making the P pillar in silicon carbide in this context. Okay, so it's much easier to make this kind of an interface in silicon carbide as compared to this kind of a device. So that's the moral of the story. And we could also study the practicability aspects modeling aspects, and also could give the design equations. So just like equations for superjunction, we could also derive equations for charge sheet superjunction. We call it charge sheet superjunction because there is a charge sheet along the interface, which acts or plays the role of P pillars in this device. So these are some of the calculations using our model, comparing the specific on resistance for different breakdown voltage from 1 kV to 10 kV of superjunction and charge superjunction, and we could demonstrate that our proposed device could lower the on resistance by 5 to 45%. So that's it. And then in conclusion, we discussed about the breakdown voltage specific on distance design trade-off and its significance in overcoming this in-house for India. And we also saw material and structure related innovations for overcoming the trade-off. Also, we discussed the contributions that we could give from our research work towards overcoming this trade-off. And these contributions were mainly two. And firstly, being we could derive closed form solutions for the optimum pillar parameters of ideal as well as a practical superjunction. And we could eliminate, using our solution, we could eliminate the 3D search approach of prior works. We could also propose charge sheet superjunction, a novel device, as an alternative to superjunction in silicon carbide material, and thereby solving the P-pillar fabrication difficulty. We could also show that it offers lower specific on resistance by 5 to 45%. So much of the results that I've shown you are from these publications. In case any of you are interested, you can look up at any of these publications. Thank you. I don't know whether it's quite early. No, right? Okay. Right. Thank you. So is there any questions? I'm happy to answer. Anything related to fab or anything related to any of these trade-offs or the scope in the industry, anything?
Excuse me. Am I audible?
Yeah.
Yeah, sir. This is
What's
Ponmalar. Yeah.
Ponmalar?
It was,
Hi, Ponmalar.
it was very. First of all, I would say that it was a very nice presentation. I can understand the quantum of the work involved, but the way you put it in such a simplified way, anybody could understand, and it was worth a Sunday evening, and that I would really appreciate that.
Thank you.
Now,
Thank you so much.
Now coming to the question, like we were searching for different materials other than silicon. Other materials are being studied. Can you just throw some light on how gallium nitride based devices are going to help up for Indian scenario or in power semiconductor devices scenario, and where do we stand with respect to global scenario in that part?
So looking at gallium, it's a very nice question. Thank you for asking. And looking at gallium nitride, there's a reason why I didn't put gallium nitride on my slides. It's basically because we were looking at very high voltage devices. So as of now, it's like gallium nitride will or is foreseeing to overcome silicon in the, let's say, below 1.2 kV market, okay? Or somewhere like 700, 800, up to 1.2 kV max. So silicon carbide has the potential even beyond 1.2 kV, up to tens of kilovolt. And the reason being that when you want to make very high voltage devices, you want to have it, you want to make those devices vertical. Okay, vertical means the current flow will be vertical from top to bottom. In all the slides that I've shown you, you might have noticed that the contacts are in the top and bottom, right? So the current flow will be vertical, and that is very crucial in what should I say, reducing the specific on resistance, having vertical devices, because otherwise, if you make devices lateral, it occupies a lot of chip space. Okay, so you need to have only when you make vertical devices, then you can have this low specific on resistance for a given breakdown voltage. So that makes silicon carbide much strong competitor, especially above 1.2 kV or 1 kV, because silicon carbide, it's easy to make vertical devices, but GaN, it's not that straightforward, because GaN is usually grown on a substrate like GaN on silicon carbide, right? So GaN on GaN is there, but it's very expensive as of now. So GaN is usually grown on a substrate, and because of which you have this material change, right? So you can't have a good vertical device on GaN as of now at an industrial level, maybe, because GaN on GaN is there, but GaN on silicon is the one which usually people work on, or GaN on silicon carbide. That's also expensive, by the way, but still having different substrate from the original material makes it difficult to realize vertical devices, and making vertical devices is critical for high voltage applications. And for GaN, coming to GaN, it is going to have a big play in this below 1.2 kV market, around 600, 700 for let's say electric vehicle chargers, which would need somewhere around 600 to 800. For those applications and all, GaN definitely will have something. And for RF applications, of course, because GaN has very high mobility, it can switch extremely fast. So in all those applications, GaN will definitely have its own advantage, where silicon carbide doesn't have that kind of high mobility as compared to GaN. So silicon carbide is not a good for RF applications and so on. There definitely GaN is going to be the thing. But for very high voltage markets, silicon carbide is a much stronger contender as of now, unless GaN on GaN, like pure GaN substrates, are available at an affordable rate for the industry. So where we are standing, we do have a lot of initiatives. We do have research groups in India. There's a very strong group in IISc working on GaN, different aspects of GaN, not just they focus on wafer growth, design, manufacturing, and everything. So there is work going on, but still a lot of scope for improvement, or a lot of potential is there, untapped potential is there. And with Indian Semiconductor Mission, a lot of these initiatives have received a lot of boost. So hopefully things would, there will be a lot of opportunities created very soon in GaN and generally about in all the power semiconductor sector. Did it answer the question?
Yeah, very much to the point. Yeah.
Okay.
Thank you.
Thank you.
And one more question is that between superjunction and CSSJ, when you have modeled, you said that you were able to reduce the specific on resistance, or you were able to predict the model by 5 to 45%. So whether that's such a large variation, what do you attribute it for? Why that 5 to 45%? That range is actually on the higher side, right?
But that advantage, that's like for certain breakdown voltages, superjunction gives only 5% advantage. For let's say much higher breakdown voltages, sorry, I'm saying for a given breakdown, let's say you're considering 1 kV to 10 kV. For 1 kV, maybe CSSJ is offering only 5%. For 10 kV, it might be offering 45%. So that's like I don't have a physical intuition about why there is a gradation, such kind of a gradation of improvement. That is as of now, it's a consequence of the, what should I say, of the large number of parameters involved, because it's like there are two parameters mainly, breakdown voltage and specific on resistance, right? So we are interested in these two parameters, and the device level parameters are thickness, doping, thickness means pillar length, width, and the doping levels. So these three things combinedly decides the breakdown voltage and specific contestants in different fashion. So it's a combination of what parameters will give the least on resistance and all those things, which decides ultimately how much improvement is possible. So to be frank, I don't have any physical answer about why there is an improvement gradation like that, 5%, 45%. But as of now, what I can tell is it's a result of a mathematically model thing, and that's what simulation is also predicting the same level of improvement gradation.
Yeah, yeah. Okay. Can I ask one more thing? Like, is it related to the performance metric that you are trying to use, like in terms of being percentage that we are trying to look into it, that this large variation comes up? If it is another performance metric, like if you really look it down into the absolute values of these numbers, because when you go down to the smaller values, and a very small change also could turn out to be a big percentage level, right? So whether anything like that has been looked into?
Did you mean that instead of looking at breakdown voltage and specific contestants, you look at some other parameter? Is that what you're implying?
No, I'm saying that when you are comparing the performance of SJ and CSSJ in terms of percentage, rather than that, if you look at the absolute numbers or anything other than the percentage, would give you better numbers? I mean, I don't know. I'm just loud thinking on that.
I mean, first, it's not very clear to me. Like you're saying instead of percentages, if you look into absolute numbers, is there an advantage? Is it?
Yeah, which is small, or because the 5 to 45 variation, any answer we could derive out of that.
So it's like what should I say? If you're looking for 1 kV application, that 5 to 45% is the if the expected improvement over a very wide range of breakdown voltage, right? So I don't know whether how fair it is to compare that gradation, because it's happening over a very wide range of breakdown voltage. If you look into any particular breakdown voltage, that's usually you want to design a device for a given application, and that application would demand a certain breakdown voltage. Let's say electric vehicle charger. It's, let's say, 800 volt device that you want to make, and then the breakdown voltage is fixed. Okay. Now the question is, you have two options. You make either CSSJ or SJ, or superjunction or charge superjunction. Which device you want to make? Then the other question is, how do you decide the parameters of these two devices? Okay. Like both, you need to have 800 volt breakdown voltage. That is clear to you, because that is the requirement from the requirement of the application. So 800 volt is fixed. Both these devices should have 800 volt. Now the question is, what kind of specific resistance that these devices can offer? And for that, you need modeling, and you find an optimal set of parameters which gives you the least specific resistance for that breakdown voltage. Let's say for superjunction, I get, let's say, 1 milliohm centimeter square, or 1 milliohm just in terms of resistance. Like it should be actually specific resistance, but let's imagine resistance. 1 milliohm for superjunction. Okay. Now, if I choose charge superjunction, you might be able to get 0.8 milliohm. Okay. So for the same breakdown voltage, by using charge superjunction, you are getting 0.2 milliohm lesser. Compared to 1 milliohm, you're getting 0.8. You are getting 0.8 milliohm, right? So that's the kind of thing that we're looking at. What the equations that we derived corresponded to the least resistance offered for that breakdown voltage. For 800 volt, how much low I can achieve the specific resistance, and what is the value of the parameters of the device that is giving me that least value. That was the thing. Now you are comparing the two optimals, optimal of superjunction, optimal of charge superjunction, and then you are seeing how much difference in the minimas are there. Okay. So that's the only thing I have. Like, I don't have any physical intuition about the improvement. Like we have intuitions about why it's why it's what should I say, better, but why that 5 to 45% gradation exactly is a consequence of something in because the dependency is not that straightforward. There are three parameters deciding two parameters. The superjunction 3 parameters deciding 2 parameters. So it's a combination of the whole thing that is deciding what is the amount of improvement that you're getting ultimately. So that's from me, I think, on this.
Yeah, okay, fine. I mean, I get the picture. No problem. No, I probably I'll take it up offline if I still find it.
Yeah, sure. Yeah, we can.
Yeah, yeah.
I will also think about it, that whether I can explain that to you or in a better way, and get myself any new intuitions out of it. Question, by the way, yeah.
Thank you, Dr. Akshay, for your detailed presentation. Actually, I have one question. Actually, it is not technical. Actually,
Okay.
you talk about semiconductor industry, and we all know that in India there is a big future. And yeah, in our participants, most of the participants are UG as well as PG students. So, what is your advice to them to get into the semiconductor industry, or how they need to equip themselves for getting into an industry? Because most of the students are going to software field, but now they are interested in this area. But how they can equip themselves? So, what is your advice to them?
So usually speaking, the core semiconductor jobs, the core design teams, modeling teams, they usually recruit at the master's level or PhD level. That's one thing. At the BTech level, it's usually very difficult to get into the core design team of the in these semiconductor devices. Usually they take master's or PhD student. For instance, my team here involves all PhD graduates. So, but at the same time, I can tell you that it's not just about device design only, right? There's a lot of the whole ecosystem around it. There's circuit design, there's testing, verification, boarding. Everything is there. That ecosystem is growing together. It's not just that just some semiconductor foundries making some device and just getting rid of it. So to make systems, you need to have all sorts of thing, right? So for instance, in Micron, the company that I'm working in, it employs all sorts of profile. Like it has all sorts of profile ranging from like it employs PhD, not just PhDs, masters, BTechs, a bunch of others. So in terms of employment, this is going to be really huge. All the scope for not just device engineers, also circuit engineers, testing, verification, all those things. But if you are specifically asking me how to get into core semiconductor device team, my advice would be to do a master's in the area of microelectronics, possibly in from a good college with a good placements. Not necessarily, but favorably, because the companies directly usually recruit from these colleges. Otherwise, you also have offline placement. You can apply through, let's say, LinkedIn, and there's a lot. These days, there's a lot of opportunity on this along these lines, right? So if you are very interested and passionate about it, you will definitely get it. Not necessarily from IIT and all, but still. Yeah, to get into core device team, yeah, masters would be very much advisable, and do internships whenever you get chance to do internships in these companies. You grab those opportunities. You keep track of LinkedIn, wherein they post all these interesting opportunities. Yeah, that's all I think I have.
Yeah, I got it. And actually, I'm talking about not into the core, because the post like verification engineer or layout engineer like that, which is most suitable for BTech students. So for that, actually they are normally going with the normal curriculum. So apart from that, what they need to equip themselves for getting this internship, even for internship. So simply, no company may take students for their internship in this area. So from your company perspective or from your experience, what you can advise them?
So I used to have some slides for that as an advice to BTech students about what they can do during their BTech times. So there I used to tell that one thing that people should be doing at the BTech level is to try for good internships. That could be through like LinkedIn or anything like that, but faculty contacts is also very helpful. Doing good internships helps you to get into or get in touch with people who can give you bigger opportunities. So doing good internships is key. For instance, I could do internships during my second year and third year. Second year under my professor at NIT Calicut itself, and from there I could, from him only I could get a. He suggested or he recommended getting an internship at IIT Madras during my third year, and during that third year only once I could do the internship, I met that professor, Professor Karmalkar, and it is under him that I did my PhD also. So what I'm saying is that such opportunities comes when you network with people, when you go around, right? So internships, I would say, is a really good thing. Second, about the projects, you have opportunities to do major project, minor project, and all during at BTech level. That also you have to very carefully pick, not just Google BTech project possibilities and get some normal, very regular stuff. You try to get into or try to do projects which is challenging and exciting. Because that gives a lot of what should I say, exposure, and if possible, try to pick, if possible, not everything is not every on every topic it's possible, but at least try to choose topics which involve slight amount of research. Not very easy, but if you get topics which involve slight amount of research, it's good. For instance, I was fortunate enough to get such projects because during my major project, my guide, Bhuvan sir, who is was very key in organizing this webinar. So he gave a topic which I could, what should I say, which gave me a lot of research opportunities. We could also publish some conference papers based on that project. So project should be taken very seriously, because that one has to see that as an opportunity to explore more, not as just a thing to get rid of and get some grade and go. And other than that, internships, projects, and electives. Okay, of course, electives. So electives also, we usually see people taking electives very randomly without some senior might say it is good, then you just take it, or your friend might take it, and then you also take it just to join. Rather than that, the electives also should be seen as an opportunity to know more about the field. For instance, I have taken a lot of semiconductor-based electives during my BTech, which had really helped me get that orientation at an early stage. So electives also, if you carefully pick and choose those electives that you take with more focus in a more focused way, that will also be very beneficial. Eventually, when you are specializing in or interested in a certain domain, you try to choose topics related to that. That'll be good. So these three things from my side, for BTech students especially.
Yeah, thank you, sir. Thank you for your detailed explanation. I think it will be helpful for the students as well as it is helpful for us also. And since we are from academia, we are not that much familiar about this industry and all. So we are getting knowledge from people like you only. Okay. Okay.
Thank you.
Yeah, thank you, sir. Any other questions? Otherwise, Kader sir, shall we wind up?
Questions? Any more questions? We don't have any more questions, sir.
Yes, sir.
Okay.
So, thank you, Akshay sir, Senior Engineer at Micron Technology, for your inspiring and educative talk on power semiconductor industry, innovations, and significance on India. Talk was really helpful in understanding about the challenges in device fabrication and trade-offs. Thank you, sir.
Thank you. Thank you so much. Yeah.
I also wish to thank all the IEEE members who have joined this meeting and all the participants. Thank you. Thank you. Close the webinar. Yes.